Welcome to today's lesson. So we are on Unit 2, Derivatives, Lesson 5, the quotient rule. So in previous lessons, we looked at strategies in order to differentiate different types of functions and even more complicated types of functions. Today, the quotient rule is going to look at differentiating functions in the form of a quotient, obviously, quotient rule. Differentiating using a quotient rule. If we have q at x, which is equal to f at x over g at x, where f at x and g at x are differentiable functions, then g primed at x cannot be equal to 0. Q primed at x can be expressed as q primed at x is equal to g at x times f primed at x minus f at x, g primed at x, all over g at x squared. Whew, that was a mouthful, wasn't it? Okay, so basically this is the general term for the quotient rule, okay? So this is how we would differentiate anything that is in quotient form. So basically a function divided by yet another function. I find the quotient rule a little bit hard to remember. So one way that helps me to remember the quotient rule is I have a quotient rule song. Okay, so here's the quotient rule song. Your teacher is not going to be singing this to you, but I will mouth it out and just say the words. Now, this is supposed to be sung to the tune of Old MacDonald, so maybe you can do that yourself. Okay, so I'm simply just going to read it. Low D high, less high D low, E-I-E-I-O. Then draw the line and down below, E-I-E-I-O. With the dx here and a dx there, here a slope, there a slope. Yes, there's hope. You can cope. Denominator squared we go. E-I-E-I-O. I usually say it with normally low, low, which reminds me that I'm supposed to square the bottom part. Okay, maybe that'll help you, or maybe you'll just memorize the equation. Look at our first example. So in example number 1, q at x is equal to 6x minus 1 over x cubed plus 4. Okay, so we want to state the domain of q at x and q primed at x. So what we'll do is we're going to use a quotient rule because we'll notice that it is in fraction form, so it is a quotient function, a function at the top and a function at the bottom. So we can use a quotient rule. I'm going to show you the long way, which is the quotient rule, and then I'm going to show you my shortcut because I can never remember the quotient rule and I only use the product rule. However, in doing the second method, my method, in which I would just use the product rule, there is a little bit more algebra, okay? That if you're more comfortable with algebra, that's fine. You can use either methods. Okay, quotient rule. Just as before, what I like to do is I like to label this top as being f at x, okay, and this is being g at x. Okay, so let's first go over to the right side here, and I'm going to say f at x is equal to 6x minus 1. G at x is equal to x cubed plus 4. Okay, let's move this over. F primed at x is equal to 6. G primed at x is equal to 3x squared. Okay. Now, I'm going to go ahead and use my song, okay, until you get used to this. So Q primed at x, and the song goes low D high, okay, low D high. So G at x, low, and order does matter with the quotient rule because of the minus sign. So there's my low, which is my g at x, d high, which is the derivative of the high, or of f at x, which is the numerator, less high, 6x minus 1, d low, 3x squared. Okay, draw my line. And I usually just say low, low, which is my denominator squared. Okay, and there you have it. You can simplify this further. So I'm going to multiply the 6 in, so it'd be 6x cubed minus 24. And just for now, I just want to do this, that you don't make a mistake with that negative sign. Okay, and that works out to be 18x cubed minus 3x squared all over. And right now, I just want to keep it as such, only because I always try to see if there's anything any terms that I can cancel out. So if this is all in one bracket, maybe there's another one that I can cancel there. Now, did I make a mistake here with my signs? And I did. Okay, there we go. Yes, okay. It doesn't look like I'll be able to cancel because I don't have another one of those x cubed plus 4s in the second term. So I'm just going to go ahead and simplify the numerator, but denominator, it might get kind of messy. Okay, so let's remove the brackets and multiply this negative sign in. Okay, so 6x cubed plus 24 minus 18x cubed minus 3x squared all over x cubed plus 4 squared. Okay, collecting like terms, what I have then is minus 12 x cubed minus 3x squared plus 24 all over x cubed plus 4 squared. Okay, and I would probably even be tempted to leave that. It doesn't look like I'll be able to cancel anything out. If you want to, you could expand the denominator, but I don't know if that will help us in this case in any way. I would consider this a fully expanded, or sorry, a fully simplified answer if you at least went ahead and tried to collect like terms and make it look a little bit nicer up here. Okay. Now another method that you could use, let's just do this as a side note here, is if you had q at x is equal to 6x minus 1, and remember your denominator here. Okay, so this is all together. You can't separate them. They're binomial, so they're not something that you can separate. However, that exponent, if you want to change it and bring it to the numerator up top, you can actually, as long as you keep it as a whole piece, change that to an exponent of -1. And what you've got there now is a power rule and a product rule. Okay. However, in doing this method, there's a lot more algebra involved, but if you are comfortable in doing so, then you can use this method. Okay. And maybe further on, for now, I'd use this, and maybe once we get into the next unit, we'll start using this a little bit more. Lastly, let's determine the domain of the function as well as the derivative. Now, this is supposed to be a q, not a g. So looking at the function, remember, this is a fraction or a quotient function, so we can't have a 0 in the denominator. So in order for us to figure out what values of x will give us a 0 in our denominator, we're going to rewrite this and set it equal to 0. Okay, just our denominator, and we're going to figure out what values of x. So isolating for x, we're going to get -4, and that is the third root of -4. The third root of -4, and that's plus or minus third root of -4. So I'll just rewrite that. X is equal to plus or minus, okay, the third root of -4. And yes, we can take the third root of, that's just a 3. We can take the third root of -4 because it's the third root. No, square root, we can't do that. Okay, so if it's a negative inside the radical, as long as it's an odd, we can actually do that. That does exist. Okay, so our values, our domain then is such that x belongs to a set of real numbers such that x cannot equal plus or minus the third root of -4. Okay, and I just include it into one statement rather than having to separate the negative and the positive. You could do that if you'd like here, such that x is not equal to positive third root of -4, and x is not equal to the negative third root of -4. Okay, I'm going to accept either or. All right, so let's figure out the domain of the derivative, which is going to be the same as the original function. Okay, so that would be the statement that you would write as well for the derivative. Example number 2, differentiate the following and state the domain of g at x and g primed at x. Okay, so g at x is equal to x plus 3 over the square root of x squared minus 1. Again, it is a quotient, so we're going to use the quotient rule. So looking at example number 2, again, we're going to label g at x and f at x. Okay, so I'm going to say this is f at x, and yes, you can skip this step. I'm just doing this as a reminder, okay? And what we'll have here is f at x is equal to x plus 3. G at x is equal to the square root of x squared minus 1. Okay? F primed at x is then equal to 1. Okay? G primed at x, okay, is equal to, well, it's going to be a chain rule, so let's just rewrite it again. X squared minus 1 to the exponent 1/2. Okay, so now let's use our chain rule. So g primed at x is equal to 1/2 x squared minus 1 to the exponent -1 over 2. Okay, so it's going to be a little bit messy, but that's okay. Lots of algebra involved in this one, which is great practice for us. Okay, so let's see now. Let's use our quotient rule. So g primed, okay, so we've got a couple of g primed at x, g primes here, but that's okay. G primed at x, okay, remember our song, it's low, which is, okay, I'm gonna use the exponent form, and you'll see why in just a sec. 1 over 2, okay, d high, which is just 1, minus or less high, x plus 3, d low. Low, low. Draw my line, low, low, which is, since it's a square root, and I square it, it'll just simply be x squared minus 1. Okay. Okay, so is there anything that I can cancel or factor out? Let's see. In doing these questions, what you want to look for is the lowest, in the denominator with the lowest exponent. So in this case, it's minus 1/2. So I'm going to factor that out. And I know it's going to feel a bit funny, but what we'll do is we're going to factor that out because it is the lowest exponent, okay? Okay, let's see what we have left. Using our exponent rules, so what we have is exponent 1/2 minus a -1/2. So that leaves us with just an exponent of 1. Okay, multiplying the 1 through, I'm just going to leave that. Minus, bringing out this 1/2 just right here. Okay. And then x plus 3, and you'll notice I'm not using my square bracket because I know where this is going. So basically here, if we factor it out, what we're essentially doing, remember, is dividing, and that's why I'm subtracting the exponents. Okay, so here, because I'm dividing them out, when I factor negative 1 over 2 minus a negative 1 over 2, which would give me okay, which is simply 0. Okay, this would mean that this entire bracket here would turn into 1. Okay, so that goes away. And then we have x squared minus 1. Okay. Okay, so what we have here is like terms, okay? So this is the same base. So x squared minus 1 is the same base, and you can look at this as if it has an exponent of 1, okay? One of two ways you can look at this is this divided by that. Negative a half. When you have a division of the same base, an exponent, you subtract. So minus an exponent of 1, which would then just give us negative 3 over 2. Okay, I'm going to go ahead and put that in the denominator as being x squared minus 1, which would change it to a positive exponent, like so. Then we're left with x squared minus 1 minus a half x plus 3 over 2. Okay, I know it's messy. There's not much we can do about this. So the only thing we could do is multiply everything by 2, and that would get rid of some of these messy fractions here, but we would have to multiply everything by 2. Okay. For now, I'm just going to rewrite this as x squared minus 1. Actually, we can collect that. So let's first move this 1/2 x. Okay. And in this case, it will just be minus a half all over. Let's change this now so that it doesn't look like a fraction and exponent. We're just going to go x squared minus 1 to the exponent 3 square root. Okay. Oops. Square root. Square root, yes. Of course, we've done that. Okay, so that looks good. If we want to, we can multiply both the denominator and the numerator and the denominator by 2. If we do that, okay, we're essentially multiplying by 1. We're not changing anything. 2x minus x minus 1 all over 2 square root of x squared minus 1 cubed. Okay, and there is our messy answer, but that is a complete answer. Okay, let me just put this x. There we go. Perfect. Just as a quick note, I did forget the squared on the x squared, so you just want to include that as well. Let's take a look at the domain and the range. Well, let's skip the range. Let's just find the domain of both the original function as well as the derivative. Okay, so the domain is our x values. Now looking at this, okay, remember it's a quotient, so we want to take note of where it is not, where it does not exist, okay, or undefined. So we'll just take a look at the denominator again. So in this case, we have a square root, okay? So let's just take a look at x squared minus 1. Well, first of all, the denominator cannot be 0, and inside the radical, we can't have a negative number, okay? So first, we're just going to look at the case in which we cannot have 0, okay? So we'll just take our function there, and we'll just set it equal to 0 to figure out what values it needs to be in order to be 0. So x then is equal to plus or minus 1. So that is the case in which we have a 0 in the denominator. But what about the negative inside the square root? When is it ever going to be a negative number? Even if we were to put in negative 2, for instance, into x, because we have a square there, it's going to turn it into a positive. So it'll be a positive number that's larger than 1, and when we minus it by 1, we still have a positive number underneath the radical symbol. What about if we put in 0? If we were to substitute 0 in there, then we would have -1 underneath the square root, and we can't have that. It is undefined. So for values that we cannot have as x, we have 0, -1, and 1. Okay, and that is also true for the derivative of the functions 1. So just to conclude our lesson for today, we're going to check our learning. Determine the value of dy by dx for y is equal to 2 minus x all over x squared plus 1 when x is equal to 0. So make your decision now. And the answer is D, 2. And that concludes our lesson for today, and we'll see you next time.